welcome, welcome. I guess since we're here at TEARDOWN, and some of you hopefully have precursors, or maybe you don't, I thought I'd just have a session about precursor hacking. So the first thing I think would be helpful, maybe just went around and heard what people were interested in learning more about. Because one of the problems of precursor, and this is one of the problems when you have a product that has a dessert topping and a floor wax, is that no one knows what to do with it or where to start on it. So, and neither do I know how to start a workshop like this. So maybe we can start over there. And if you're just here listening in, just say pass. But if you have like a specific thing you want to get into more, go ahead and call it out. I mean, I have, just to give you the list of things I'm prepared to talk about, we can do everything from like customizing the case, talking about the electronics, the circuit board, my workflow. We can talk about Zeus. We can talk about the embedded controller. We can talk about the Wi-Fi stack. We can talk about the libstud. We can talk about Rust problems. We can talk about like, you know, all kinds of stuff. So anyways, go ahead and just say what you're interested or not interested in. Yeah, sure. Is the microphone working? And while you're doing that, I'll also pass this around. And everyone can feel free to just grab, I have some extra internal circuit boards for the precursor here, which you can just grab one of because I have lots of extras of them. And I'll tell you more about why you might want one of these in a minute, but just go ahead and grab one as you pass the mic around.
Okay, so I have no questions. Didn't know even Precursor exists until 5 minutes ago.
Okay, sure, great, welcome.
All of those things you described sound very interesting. I'd be happy to learn in-depth stuff on any one of them.
Okay,
Yeah.
Wonderful.
Yeah, the same.
Okay.
More of the above. Also, how the Rust stuff is kind of interesting as well.
But Rust is interesting too. Okay.
I work here. I also have a precursor. I unfortunately forgot it, but I'm most interested in kind of the FIDO2 and the secure.
Oh, FIDO2 stuff. Okay.
Well, and just key security.
Okay. Sure. Okay.
I've only seen Precursor from a distance, really, so just because I'm here, it's an opportunity to learn a bit more about it. I would love it if you passed one round, because I've never physically seen one.
Sure,
if that works.
Yep.
Maybe you go first. I've never had a precursor, but I thought this looked cool.
Okay.
I make non-rectangular phones for non-rectangular people, starting with the circle phone. And I've had lots of problems with people adopting our phones as well, getting them over the sphere, even though we run Android. So
I couldn't quite hear what you're. No, I'm going to stand up close so the mic wasn't projecting. Can you say it again, please?
So we've run into the same problems too, having people adopt our phones because of, even though we say it's Android 10, it's still really hard.
Yeah. Okay. Yeah. Okay.
I'm just here to learn more about the precursor. I got to handle one in New York City a couple months ago.
Okay.
It was cool.
Cool.
Yeah, same. I've seen it for sale. I've seen some of the marketing for it, and just here to learn more about it, and hopefully put my hands on it briefly.
Okay. Great.
Cool. I've followed Precursor for a fair amount of time. I'm most curious about just kind of RISC-V Rust interfaces, and how do you extend the Rust environment to new platforms?
Okay. All right. Rust to new platforms. Gotcha.
I'm interested in the entry-level learning and also the plausibly deniable database.
Oh, okay.
Find out more about that.
Cool. All right. Yeah, I'm happy. That's a kind of a soft spot for me. I'm happy to talk about that one.
Yeah, I mean, I'm here to get to know more about the device. It's the first time I'm hearing about it. So,
okay.
Yeah.
All right. Neat.
I'd like to know how to get into the Precursor App Store, get through that approval process. No, I'd second the plausibly deniable database and the app workflow, the Rust app workflow especially.
Sure. Yep. Okay. And this dude's manning the camera. Got it. Let me just get a precursor to pass around. I am just making sure. I have one here we can use, but I just want to make sure, because I'm actually going to do something a little bit. Anyways, this is my actual password vault, but I'm relatively confident that you can't get my passwords right now in the mode that it's in, so I'll go ahead and pass it around. There is a little bit of, so the whole idea actually behind this is that it is using the plausibly denial database, and it's in a mode now where I could hand it to a customs officer and they can inspect it. So there will be, you will see some entries in here that are like my global entry number and a few other things, which basically you have to hand over anyways. But you can kind of get an idea of the mode that you can put it in for, like, you know, inspection by officials or whatnot. So that's running the Vault application right now. You should be able to poke at it and it won't fall over too hard, but anyways. So, all right, maybe it's worth spending about 15 minutes. I will give you like the rush overview of all the things inside of it. And then we'll drill a little more into sort of, it sounds like people are interested in Rust and the RISC-V stuff. And so we'll get into those. So we do have a screen here behind me. And how do I put something on? Oh, good. Look at this. So, hello. This is the case. It happens to be, of course, open source. You can download everything. It's on our GitHub repo. I'm just showing you kind of just to get you an idea of the design process here. So this thing is a full model of the device. You can see that all the components are modeled through. So we can, it was very hard to get the clearance right here. And so, of course, we had to get everything modeled down to the component. Let me see. There you can see the cross-section view of the device here and what it looks like going through the device. So if you want to go ahead and hack the device a bit, the thing I want to point out is I did leave this part here. This back piece is a plastic piece. It's a radome. It's meant to actually, it's actually just big enough for you to stick a camera in there by intention. You could drill it out, put a little camera in there, and that little PCB I'm handing around right now is a replacement for the Flex PCB that's inside the device. And you'll see that there's actual pins labeled on there. So you can, there's actual solder pads you can actually solder down, and they go directly to the FPGA. And the pins of the FPGA is sufficient for you to like do a small CSI interface to a camera, or you could put an NFC device in there, or you could do I2C, your favorite sensor, whatever it is. And so if you want to go ahead and play around a bit with the hardware, you could do that. It was also designed with the idea that if you wanted to put an LTE module in, you would get a smaller battery. You would sacrifice some battery, but you could just shove the LTE module here near the radome, and then you would just do AT commands over UART to it or something like that to go ahead and get LTE. So it was kind of designed with a little bit of hackability in mind, despite being a very, very compact mobile form factor. 0 people have taken advantage of this, including myself, because it is a very small, fussy case, but I thought it was worth pointing out that there was a feature that I had designed into it. That's it for that, unless anyone's had any questions. This is the circuit board design. I use Boo Altium. It's not KiCad. Sorry, guys. I know this is an open source conference, but here I am with my proprietary tools. It's, you know, it's a PCB. It's a HDI, high density interconnect PCB. So I use, this is the via in pad technique here to fan out. This is a 0.4 millimeter CSP. And so I'm able to do blind vias to fan out the CSP. And in doing a mobile device like this, you're required to do HDI because you can't get good parts for mobile devices that don't assume you have that technology. So that was kind of mandatory. And we had a session yesterday where I'm trying to encourage more people to get into using this, this technology because it's pretty enabling for doing your own mobile device. Sorry? Can we see test jig V1? Sure. Test jig V1s. This is the actual test jig design for the device itself. It's a little faint because there's a little sun coming in, but you can, back here I actually have the outline of the PCB drawn in purple. These are the breakouts for the all the wires for every single voltage to the bed of nails that comes down here onto the device itself. This is a battery simulator. So this here will actually simulate the battery both in high load and low load mode. So I can simulate charging and discharge. Dummy loads for the speakers. Raspberry Pi plugs in up there. There's a USB interface up top. I have an audio jack that loops around into the device, so I actually test the audio. There's a full FFT, plays tones, cross tones, and stuff like this during the test routine to make sure the audio is okay. And then power supplies and voltage translators and stuff like that. So, yeah, I do. I should have a photo of that. Let me just see if I have one in my hot context thing here. Yes, you might be in luck. May not be a great photo of it, but hey, look, I'm on an SMT line. Let's see, does the photo, the photos are helpfully showing up over here, not over there. That's the SMT line that we use to build things. Let me grab this thing back over here so I can throw photos up. Let me see if I can find the test jig. Test jig, test jig, test jigs. A picture that kind of shows you most of it. This is the one without the test pins coming down on top. So there's actually I have two versions of this. One of them has the voltage things that come down, and the voltage test is quick. They stick it in, make sure it's not going to catch fire, and they move it on. So I have one station that does the voltage test actually. It's like am I going to catch fire test? And then this one is the firmware burning station. The firmware burn takes a long time, so we have many more of these. I replicated this several times over. I actually do all my pulls for the firmware from GitHub directly. So the stuff that is, you can actually see what I'm running on the factory tester in our GitHub repo live. And I literally use git pulls to pull it. So when fucking GitHub messed up their keys, that was really annoying and still is annoying because I'm probably gonna have to fly to Korea to fix that because I did not ever consider that GitHub would mess up their keys as part of the scenario for my routine. Anyways, so and so this one here is, yeah, you can see the battery simulator, whatever it is, and like every time they update the device, I have there's two buttons. There's one for go and one for function. So this is one of my principles of test rig design, make it very simple. And when it runs, it just says, the test. And when it fails, it'll say which chip failed, like check U11K, chip this one, audio failed, whatever it is. So it'll print out the message. And then every time they do a firmware update, I have them send me the hashes that got pulled into the jig so I can confirm that it's all correct. And then there's some telemetry back to my server in Singapore so I can verify that nothing blew up along the way.
So you're using a flex set, you don't have a bed of pins, right? You're using the flex.
The flex is actually, this is the normal debug port on the device itself that it exists on all devices, and that's where the firmware gets loaded. So this one's just the firmware loader. Sorry, this is going to be like a selfie shot. I think this is probably the only one I have of the whole assembly there. Let me see if we can zoom in the background here, the interesting bit here. That's the one with the bed of nails on it.
With the beer tap press.
Sorry?
With the beer tap press.
Beer tap press, yeah. So it's the welding clamp, actually, is what it is. Yeah, but it's a welding clamp. So they're originally developed for welding. So when you're welding a piece, you want to put the workpiece down, you fold it down, and it holds it in place. So they originated from welding clamps, but now there's a whole sub-market for these, so they call them test jig clamps, but originally welding clamps. Yeah, so this one has the bed of pins on the top. You can kind of see the wires going down the side, and I have a whole bunch of the other ones here that I use for firmware burning. So this is my last trip to Korea. I was just the big reason I go to the factory is to actually maintain these guys because they're really complicated and a lot of effort. And one of these actually exists in Singapore. If you go to ci.betrusted.io, let me go there on this website here. Sorry, 1 second. you can see the status of our CI system. And this is actually hardware in the loop. So when we do like the CTAP2 tests for compliance testing on U2F, we actually run the full CTAP2 on the live device on one of those jigs. It's fully scripted with TCL and expect. Every time we do a build of Zeus Core, it runs the factory test, which is the actual test that we run in the factory to make sure it passes the factory test. Then it does like an extended test where I do the PDDB. I do like a backup test to make sure I didn't break backups. Like there's a whole bunch of just automated tests that we do on the firmware side to make sure things don't break. And so this is like, it's all hardware in a loop. I use that exact jig. So basically, whenever we go from a release that we're ready to push, I've had very good luck so far in not breaking the factory, which is like super scary that you ship something over and a bunch of units start failing. That is like a nightmare scenario I really try to avoid. So that's our internal development process, if you will. So.
Does the factory rely on being online?
Absolutely. This is one of the benefits of being in South Korea. So it's not behind the Great Firewall. I have a gigabit line to the factory I can SSH in. It's not filtered. It's like great. Yeah.
So you have your own line to the factory?
It's the factory's line. Korea has great internet. And it's not filtered and it's awesome. And yeah, I can get hard lines to all the test jigs. And the other nice thing actually about working with the Koreans is that people in university learn Linux and command line tools as well. So most of the managers on the floor are comfortable typing command line. Whereas in the Chinese factories, typically they aren't, I find. So in the worst case, I can harass them to type a few command line things into a Raspberry Pi if I really get stuck. So it's like super helpful as well. Not trying to be like you should go to Korea kind of person, but that's one of the deltas I've observed.
Sorry, can I ask another question?
Yeah.
So that photo you showed, right, the selfie and we zoomed in on the background. Yeah. So there were 3 jigs. So one's doing like power, and one was doing that debug interface, and one's doing the bed of nails. So every board goes through each one of those.
No, there's only one that does a bed of nails because it's very quick. So the bed of nails is actually like that little OLED display. Actually, just live shows every single voltage on the device. So when it's not plugged in, it shows everything's failed because all the voltages are off, right? You put it down and it shows you the voltage, and there's like a little like white-black test. It's not red-green because it's a black and white display. And so the operator plugs it in, puts it down, and if any of the voltages are out, it's going to catch fire. Don't go past go. Look for shorts, and then so basically it's a pre-screen before you get into firmware burning. So you don't want to spend 10 minutes of the device roasting itself. It's just it's a lost board at that point in time, right? And then it goes to 3 identical jigs that don't have the thing on top. And the part of the reason I don't have the pins on top is you need to plug all the cables in, and the operator's hands will be stabbed by the pins. It's not very unpleasant for them to have that. So I actually take the pin housing off for the good of the operators. And you don't need to do that voltage test anymore. And it's a very long-running test. It takes about 5-6 minutes to burn the firmware. And then after that PCB screen test is done, it gets fully assembled, and there's a final, what I call an OQC test, where you go ahead and all the keys have to be pressed and has to associate with the access point, do some pings and stuff, just to make sure they didn't leave the antenna unplugged, that sort of thing. So,
how many have you made? How many have gone through that process?
About 1,000 now, I think, overall. Yeah, roughly, a little over 1,000, I think. So, it's enough that I found weird. I can really give you like war stories about weird problems we're finding now because we're doing full different lots of material. I want to point out that the 2 flex connectors that I have on the inside. So this is the one that is you observe there's a cable that goes to the test jig, and this is the debug connector. This is what you would plug into with the Raspberry Pi hat if you got that. And this is basically the way you unbrick your device. So if you go ahead and screw everything up, like you've just screwed up your FPGA, you self-destructed the device or whatever it is, and you want to recover it, this is the header that you use. It has JTAG for the FPGA, and it has access to the embedded controller's SPI-ROM, so you can program everything directly, even if everything doesn't work. And it also has a pair of UART headers, so I can talk to both the embedded controller and the main CPU through this. And this is the internal. This cable here is the one I just handed out. So you can see this one here faces into the battery compartment, and it's basically a hack connector. The main reason it's there is for the power pack voltages, right? That's really the only thing that's in there in the speaker. But you can see I have these GPIOs available. I have an I2C in there. I have the vibrator motor drive, and also I have a charger temperature sensor wire. But there, the pinout is chosen so they actually you can run differential pairs to it, and you can like potentially put a USB PHY in there if you wanted to on the FPGA, because an FPGA you can do anything you want. And also one of the pins can be used to one of the analog A to D converters. So you have an analog input available there if you want to just put an analog sensor on the inside. So it's all there. You have the header. You can solder to it if you guys want to hardware hack. But I won't go into that too much because it seems like more of a focus today on the other systems. Okay, that is the quick tour, I think, of hardware bits. I'm going to move more into sort of the firmware stuff. Anyone have any questions? Yes?
Sorry, it's a boring question, but I was interested in the keyboard.
Yeah.
Like, where did you get some keyboard? Is it from somewhere? You found these, you sourced them?
Yeah, full custom. It's a full custom keyboard.
Oh, wow.
So the process is that, so actually if you buy one of these, you get 5 overlays inside. So the idea is that you can remove the bezel, 6 screws on the top, and the keyboard itself is held in with 3 screws. And the way you change your keyboard layout is you take the physical overlay out and you put a new one in. So I ship with a QWERTY, a Dvorak, a Xerte, Quartz, so it's French, German, Dvorak people like me, QWERTY normal people, and then a blank one, just a pure black. So in case you want to do Colmac or something like that, you could use a white Sharpie or something and write your keys on it. Or if you just want to be super elite and dark, you can just have a black thing. I know where the keys are, right? The guy is it's a really tiny event. I mean, these keyboards are very hard to source now. The guy has a really tiny shop, and the process is it's a sheet of polycarbonate onto which they build up resin. Just a resin through a UV cure process. So this mold, they basically pour the resin in, they lay the sheet on top of it, it goes a UV curing machine, and you can get about 1.5 millimeters height for the total key height. And then they cut it out with a CNC, silk screen color on the backside, and then they laminate onto it these little polycarbonate nubs that go to the dome buttons underneath. And then we have the dome button sheet itself on the keyboard, which is a sticker full of dome buttons. And it turns out that all that stuff is really fully amortized and depreciated, so you can get dome buttons and all these things really cheaply. You just have to find the right vendors for it. But they want enormous volumes. So I actually had to buy 3,000 of all these before that's all the crowdfunding money went just to, I'm buying all the keyboards I'm ever going to need for the rest of my life from these guys with crowdfunding money. But the per unit cost is really low, which is why I just throw them all into the box. And when you buy the overlays on Mouse or Crowd Supply, all that price you get charged is all just shipping and handling. Like the product cost is de minimis. That margin is all just like pays for this conference and these guys' salaries and like some guy in Texas to put in a box and then postage. That's just the cost of shipping air basically. So, yep.
I was just curious, like when I tried typing in different letters there, it was all sort of jumbled. Is there a reason why it's doing that?
You tried.
It's
jumbled? Yeah.
To punch in some values. I don't know.
Monkeys are just
yeah. So I was just curious, like, sometimes it was, if I press the key Q, it was printing exclamation.
Oh, if you press and hold, yeah. If you press and hold a key, it'll get you a different thing. But you might have, the layout might have been swapped on it. Oh, okay. I think is what might have happened. And also, it looks like someone did manage to crash it. Good job. I need to find the little pin to reset it because, does anyone have like a paper clip or something? I didn't bring one of those. Very good. I don't know how you guys managed to crash my device. That's what happens when you hand your device around, right? I have the nerve pinch. I got it, hopefully. Okay, yep, it's back. Huh. I wish I knew how you crashed it. Who crashed it? Want to know? Sure, you can pass. Oh yeah, someone changed the key layout on it. Yep. So let me see. Let me swap the keyboard layout. Probably someone was just playing around with the keyboard layout and swapped it to something that's not the actual keyboard layout, which is why the keys came out jumbled.
I mean, it might be.
So someone actually.
I might be the person who did that.
Someone actually changed the key layout.
But do you find you can type pretty fluently on that? Like you can find out text messages real fast?
I'm okay with it, yeah. I think it's not for everybody, to be honest. It's not like I gotten used to it, but I think a lot of people complain about the ergonomics of it. The small keys, yeah. I have heard from people that is one of the feedbacks that we're trying to.
Think about these, I'm sorry, there's a naive question.
Mm-hmm.
Naive question, but could you use a BlackBerry keyboard? Could you use something that's already in market and get cheap?
Yeah, we thought about using like a BlackBerry keyboard, but the problem is then we're kind of limited, but to how many of these we can source, right? Because they're BlackBerry keyboards and they're not. Okay, the keyboard layout's fixed.
Can you pull out the
Oh, I don't have the Braille model with me. Yeah, we built a version of this that has Braille, so it's like there's no display at all. It's just like a solid screen, and it vibrates, and you can type Braille, and it has like the 6 keys on it. But I didn't bring that.
Braille, yeah, with the Braille display, with dots.
No, it doesn't have it. We actually put text to speech on it. So actually, all the menus speak to you with text to speech. And I don't know if you've heard like the text to speech that blind people use, but it's really fast talking. Like I can barely understand it. But the guy I was working with, like, yep, this is how I like it. So, yeah, and we routinely test the text to speech. That's part of the CI loop. So it's still working, even though we don't have a huge like blind user base. But there are a couple Braille units in existence, and a blind guy uses one, maybe. Hopefully he uses it. I don't know. I don't really follow up with him regularly, but yeah.
I'm sorry, it didn't make it all the way round, if you don't mind.
Oh, it didn't make it all the way around? Okay, sure.
What do you find most of the users in Precursor use it for? Since there are 101 possible users.
The primary use case that I've seen, I mean, it's all driven by software, right? So the one piece of software that's most complete is the password vault. So the Vault application, which is one I left running on it, has U2F FIDO2, so you can use it as like your authenticator token. Has TOTP, so the 6-digit rolling over codes, and it has a regular text password vault built into it. Some people have added to it a Matrix client, so you can actually do some chat on it through Matrix. I think some other people, there's a couple other applications I've seen, like just people just developing stuff on the side. A guy's trying to port Signal to it right now. But I think primarily it's been for that one app, which is the most finished thing that we have. And the other thing people, I think, ostensibly use it for is like, I want to learn to code Rust. This is a great excuse to learn how to code Rust. So, yeah.
Thank you.
Yep. All right, so we will descend briefly into the layer of hell known as the FPGA design. I guess we'll start here. This is the source code for the RISC-V CPU. And why is this? Oh no. How do I get it out of this snap mode? There we go. Maybe you can see this? IDE? Okay, yeah. Great. So we use a VEX RISC-V CPU. You can see everything. We have a fork of it for our own use on the device here. And so let me see. Where is the actual fork that we're using? I won't bore you with this too much if I can't find it. This is not the exact one, but it gives you an idea of it. So we can define things like how big the cache is, how many lines we have on the inside, where the IO ranges are, what branch predictor we use, how many multiplier plugins are in, all this sort of stuff. So that's all something we configure. One of the hints that I learned the hard way is that, so there's one guy who basically writes all this, and he uses an IDE called IntelliJ. And if you don't use his IDE, his code is really hard to follow. Like, I'm like, how does this guy even code in this language and whatever it is? And until this thing gives you the pop-ups and the click-throughs, you're just not going to follow the code. So really, I have an IDE just for hacking on his code base. So if you want to go ahead and customize the RISC-V CPU, you can do this. It's in a language called Scala. It's like a one left of Java bespoke language with this tool called SBT. Complicated. If you want to build it, I'll walk you through it. But you can build your own core, which is really cool. And then we use, I have a lot more pixels on my screen than this has. This is the LIDX file. So how many people here know what LIDX is? Anyone? Okay. So LIDX is a Python-based language for doing hardware design. And so this here is Python. You might recognize, yeah. Is this font just way too small? Should I just make this, try to make, you guys can see it? Okay. So yeah, I mean, it's Python. You can see all the imports and stuff. These are like the pin definitions for all the ports and stuff is an array. And then, yeah, like Python, all this Python. So if you want to go ahead and like say add another UART into it, you can go ahead and just throw another UART in. We have a UART mux, and you can have like an extra UART inside your device. Or if you want to go ahead and create an interface that goes to an LT interface in the inside or a camera interface, you would start here. This would be your on-road for hacking it. You run the script. It will call Vivado, which is a proprietary tool, to go ahead and do the compilation of the assembled Verilog output file, and I can show you what that looks like a little bit. So this Python compiles into Verilog. Oh, here, it happens to be right here. I was looking at it. So this is the actual Verilog description of the sock itself. So these two windows are like logically equivalent, but one is basically transformed into Verilog, and this gets plugged into the Vivado compiler and turns into an SSE. You can see all the bits and pieces. TRNG, blah, 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 all that stuff. So we have like dual TRNGs. We have like a local ring oscillator. We have a avalanche-based ring oscillator. We have a crypto accelerator. We have AES acceleration. We have a whole bunch of stuff on this thing. So anyways, that's the FPGA design. So you can go ahead and play around with that too. And then we can move more into the Rusty side of things. So, by the way, all this stuff is on GitHub. Let me just show you what the GitHub repo looks like. You can see, let's see.
Which functions does the EC do?
The functions of the EC are basically, the point of the EC is to be a power controller for the system mainly. So when the system is in this mode here where the screen is like showing this is a memory LCD, so this consumes almost no power. It's basically like e-ink. And then in this mode here, the EC is actually on and waiting for the wake up key press. It can also actually talk to the Wi-Fi chip, so you could potentially get like a packet from the internet to wake up the system as well. And that does the expensive boot cycle to get the SoC running and that sort of thing. And so that's its primary responsibility. It's a pretty small code base, actually. No, it's untrusted. It's an untrusted device entirely. It exists outside of the root of trust. And it has a completely different style of code base. The code base is also in here. I'll poke on that briefly in a second. But so this is the main repo. It is oddly named Be Trusted because that's what the project was originally called. And that's actually, from an overall project management standpoint, we want to build something that is not a developer tool, but something anyone can use for trust. But this is not that. This is a developer thing, so that's why it's called Precursor, and everything's domiciled in this repo for that historical reason. There's a wiki. I recommend you go here for all kinds of documentation. It tells you how to like get started, our matrix chat, how to update your device, how to set up security, passwords. If you want to go ahead and load apps, the App Store, whatever it is, the instructions are here. tells you how to do Hello World, all these kinds of things. And then we have like a ton of documentation on the OS. We have a Rust book. Where is it? The Zeus book. So this is a book which kind of goes through the whole system architecture of the kernel, gives you stuff about like how the system starts, talks about message passing, how to do the build system, blah, blah, blah. So there's a lot of documentation here. It's a little bit dense reading, but if you have any questions, typically that would be like one of the first places that we refer people to for these kinds of things. GitHub.com. All right. And so everything is in here. So Be Trusted Hardware has all of the hardware design files. So this is like, you can see the bezels here, the case designs, the internal FPCs, revisions of the motherboard, the hat, like everything. So if you want to do any of the hardware hacking, the Braille variants in here, all that stuff. What? Should be, yeah. Let me see. Case v2. Step files. They are step files, which you can then import into SolidWorks, which will have like, if you want the actual raw SolidWorks files, I can send it to you, but actually the SolidWorks files are kind of shitty anyways. Step, I think, is better for interchanged, to be honest. This is the embedded controller code base here. So you're talking about the EC. This one is a merged code base. So it's both the FPGA design and the firmware in one repo, because it's small enough that we can do that. That's rational. You couldn't put the kernel and FPGA in the same repo because it just got too unwieldy. Like, it just didn't make sense to push everything into one. But this one's really, really lightweight. It's just a tiny RISC-V, and the actual, it's so small I can even show you the code right now. Here, it's just these code modules. It's so tiny. It literally is just a main loop. It starts with like, initialize time, get your uptime start I2C, run the charger, and comes down into this loop. This is the main loop, and it just gets messages in, handles interrupts, does DHCP, looks for imutap handler, has a little parser, and then all the commands that it can handle from the host CPU in a big loop, and that's it. Like, it's just one big event loop. That's like the whole structure. It's all in Rust. Yeah, it's super simple, right? This is like about as simple as you get for an embedded Rust program, and it's intended to be very simple. Okay, so that's embedded controller. There's the book, the wiki, the sock is here. Like I said earlier, if you want to go and hack on stuff. Let me see. The VexRISC core itself is here. This is the Scala file for it. So if you want to go ahead and build your own Vex, it's actually all just sitting here. And there's a little script you can run, build.sh, which it looks really simple. This is like all these tools, they look like one little command, but this will end up pulling down like gigabytes of libraries and take 20 minutes to run, and it'll fail 5 times through because there'll be dependencies that don't link and stuff like this. It's a whole thing. Looks simple, but anyways. Yep. And then the actual, there's a block diagram of the sock here. So yay, hey, documentation. You can see what's all on the inside of it. So there's the core, USB debug, cryptography engines, TRNG, SHA-5 engine, Curve 25519 engine, audio, memory LCD, external RAM, and a whole bunch of other peripherals. So it's we have documentation, kind of. And then let's get into the Rust stuff for Zeus core. I guess maybe we start at the beginning. Life starts at the loader. And I can show you exactly where the beginning, very first line of code starts. So we use all inline. So basically, as much as possible, this is all Rust. There's no like C trampoline, there's no libc. So one of the lies of Rust, and this is actually very frustrating for some people who do embedded stuff, is that Rust is actually a shim on top of C. It's a very fat shim on a very narrow layer of C, but if you write Rust for any regular big iron computer, when you do like call to libstudnet TCP get or whatever it is, TCP, it actually calls libc underneath it. It's not native Rust. When you allocate a new vector, it calls cmalloc underneath. It's actually using the system cmallocator, right? Which is really, really frustrating for a lot of people who want a pure Rust system. In Zeus, we do it fully pure Rust. There's not a line of C in the system. You don't have to install a C compiler to build our system from scratch. So the very, very first line of code is using inline Rust. And this is it. Yeah, I think this is it. So this is the start, __ start. This gets located at the reset vector. We set up some trap handlers. We put a stack canary for the loader to make sure it says, let's just see if we overrun the stack at that point. Set the stack pointer, install a trap handler, and then jump to the loader. That's it. That's the whole preamble from the very first instruction, right? And then at this point here at Rust entry, we are now running Rust code, which is located here in main.rs. Oh, there it is, Rust entry. So then this is the loader, right? So the loader is really, really complicated. I'm not going to go into all the details of it, but one of the things you need to know about our system is it uses virtual memory. So we have an MMU. How many people know what virtual memory is? Okay. How many people know how to, have you guys ever done the whole like I start in real mode and then move to like virtual memory mode later on, or machine mode to virtual memory mode later? Okay. So there's this thing that happens where like your system boots and everything is physically mapped. And then at some point in time, your address instruction space goes to virtual memory. So all of a sudden, when you were at instruction 4000 or something, it's actually located somewhere in high memory. And there's this magical moment where all the offsets change, the whole world changes, and you have to set up for that. It's really mind-bending to set that up. So basically what this is a piece of code that takes every single server that we've linked in, figures out where they should be located in physical memory, creates a page table mapping for every single one of them in a page table that we're not using yet, runs all the way to the end, and then it does this thing where it says, okay, I'm going to cause a fault. And when you return from this fault, you are going to be in virtual memory, and this is my program counter. And so it then causes a fault. The fault handler says, okay, just return, it's fine. And then you're all of a sudden now in virtual memory mode, and we've closed the door behind us, so we can't go back to that, and then we're now in secure state. That's what this whole loader does. That's the dance that it does. It's mind-numbing code. It's very hard, but it's kind of cool when you understand how it all works. There are cryptographic signatures on all of this. So we have the secboot module, which we do an ed25519 signature. There you go. We actually check the key signature here, and we actually have 3 different keys. You can see the code page. So if you self-sign, if we use a self-sign key, this is so, sorry to bore, tell me if this is boring to you, if you guys really want to know about the secure boot process. You guys want to know about secure boot? Okay, secure boot, right. So the idea is that you start and the FPGA has a tiny bit of ROM on the inside, which has its own secure loader. And that's supposed to be trusted. You can't, the very, very, very first instruction you run, obviously, it has to be trusted. You can't have, that's just the way the world works, right? But the first thing it does is it goes ahead and reads out the next blob that's going to run, computes an ed25519 signature on it, and makes sure it matches the stored signature, right? And if that checks out, it loads that block, and then we do that for the next thing, and so on and so on and so forth. So this one, basically, the model we have is we have 3 different signatures we allow. One is a self-signing signature, one is a third-party public signature, and the other one is the developer signature. So everything that we release, when you get a firmware update, it's signed with a developer signature. Anyone can actually sign with a developer signature, right? And if you look at a device, let me see if I have a demonstration of this here. Okay, so this one is actually one that I'm doing development work on. If you look at the very, very top, there'll be like a little small line, a hash mark on the top. And that little hash mark, so you put like a very visible thing through the status bar, to indicate that you're running a developer image. Because anyone can sign it, and then someone could take your device, put the developer image in, and then not tell you they did it. And that is enforced by hardware. It's actually like you can't undo that. You can't overlay it. It's going to be like this black and white hash up there. So you can't pre-compute an XOR, then try to put bits there and say, oh, I don't have the hash because I'm hiding it from you. It's like there, right? So a lot of people, when they first get their device out of the box, my device is broken. It has like this little hash mark on the top. It's actually a feature, not a bug.
So can you help me understand why using secure boot in a completely open source?
Because the idea, it's completely open source, but in this case, the secure boot is not to protect you from, keep you from running anyone else's code. It's to make sure that the code you're running is your code. So that like the scenario is like, I just passed my device around the room. You guys have all handled it and whatever it is. One of you could have actually just plugged it in and put some firmware on it without me knowing. If you did that, the only way it would boot and run is if you had this developer signature on that. Anyone could get the developer key and sign it. However, when I turn on the device, I would see that hash mark on the top and know that someone's tampered with my device. So the reason why we have the self-signed public key is that when you do the first, there's a little ritual you go through, you put this root password in and it creates keys and stuff. It actually creates a cryptographic key that only exists in that device itself. It's nowhere else in the world. It's actually inside of its root enclave. So no one of you would have that key. And then so when it boot back into this mode, I would know that that's the case, right? So that's the main reason we have the secure boot, is to detect, tampering or that sort of thing.
I was just wondering how you put that key in the device in the first place.
The secure boot? Yeah. So it's an interesting question. Another one of those like little guilty, like I really went too far down the rabbit hole doing this thing. So the actual key ROM itself is, you asked, so now you get the answer. I'm going to bore you with the answer. I have a helpful slide for this. GitHub.com, betrusted.io, SOC. Inside the system on chip, we have this. This is the key ROM. So it's a 256 by 32-bit key ROM, actually built into the hardware of the FPGA itself. It's not like burned into the external flash. It's in the bit stream itself. And this is encrypted with the FPGA's AES key. There's an internal fusible AES key inside the FPGA. So it's protected by that key. When you first initialize your device, we actually create, using TRNGs, a ED25519 key, which is just any random number, 256 bits. And we actually, through the F4PGA project, they reverse engineered the bit stream of the Spartan, the 7 series. So we actually go back into the bit stream and patch their key into the bit stream of the FPGA itself. So if you watch the little progress bar where it's updating, it says I'm patching the gateware. What it's doing is actually decrypting the gateware. So your gateware comes encrypted initially, but the key is all 0. It's the 0, it's not encrypted, but I mean, it's encrypted, but encrypted a shitty key, right? But we do that because we want all flows to be encrypted, even if they're not encrypted. And then it goes ahead and patches that to the key that you store in here. It's actually the multiple keys, but we'll just say the key and stored in there. And then re-encrypts the thing to that key, and then you're booting at that point with your key located inside this hardware key ROM device, right? And so that's actually located physically in the hardware. It's not like located in the file on the disk or anything like this. It's burned into the SoC. Yeah, that was like a very deep rabbit hole to figure that out, because I had to go into reverse engineering the bit stream and patching stuff and all kinds of crap like that. It was like fun, but maybe not a great use of my time. Yes, so that self-signed key is considered to be the trusted key, right? So that's when your top bar line is clear, right? We have an option for a third-party public key. So if you don't want to compile code yourself and you want to trust someone else, you can say, I'm going to load this third-party public key into the device, and I'll trust anything that comes from them. And I'll also have a clear boot bar if it comes from that person. So far, no one has stepped up and volunteered to be essentially a certificate root for this blah, blah, blah. because it's hard. You have to trust that person. They have to have like some procedure for storing that key. We have to do signing with them, all sort of stuff, but it's built there, it's in the flow. And then finally there's a developer boot key, right? So that's kind of like the 3 keys that are built into the bootloader. Other small kinds of interesting things in here is that when you first turn on the device, you reboot it, there's a tiny, tiny, tiny little graphics engine in it that can go ahead and render text to the screen. And it turns out one of the Rust's Achilles heels for small embedded systems is that when you do just a simple thing like, let me give you an example of something that shoots you in the foot. So here we actually, like, so for example here, print line, this macro here, print line, check fail, blah, blah, blah. This looks really, actually this one here, this one looks really innocuous. Sign length -4 is, you know, this thing substituted into here, right? That turns into like 4 kilobytes of code or something like this internally. Like the Rust formatter is like really, 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 really heavy because they have to check all kinds of cases. They have to deal with UTF-8. They scrub things. They go byte by byte. They allocate memory. It's like they're terrible, terrible, terrible things. And so when you are building for a small embedded system, you have to really keep the amount of like format calls minimum. And so in the loader, we are very restricted in the number of format calls we use. We're actually careful to make sure we don't use, like for example, if we don't use hex digits anywhere, it'll optimize that out. But if we even have one call that has hex digits, and we only have the whole hex library pulled into format, and it's not even part of our main code base. And so when we first compiled this, half of our code was just format code because all the debug symbols that were in there, it didn't fit, and so we had to like trim that back. It's just one of those like little annoying things about Rust. Okay, so that's the bootloader, done. Let's move on. We get into the kernel, and maybe it's better to show it inside GitHub because then you guys can know where the code is instead of looking inside my IDE. Let me see if I can navigate this by GitHub and not get lost. Where's my cursor? Here it is. Here it is. All right. So inside Zeus core, I'll go very briefly to the kernel, then we'll talk about apps, because I think that's where people really want to get towards. So kernel, you boot into the kernel, and how many people here write Rust? Okay, actually, so it's helpful for me to even just tell you the structure of a Rust project, so you know what I'm doing. Okay, so every Rust project has a manifest file called a cargo.toml file. This guy here. This is where you start in a Rust when you do a Rust program. This is the kind of first thing to look. It has all the metadata, like what it is, the revision, versions and stuff, and it defines all the dependencies. I've never used npm, but here it's a little bit like one of those package manager type of things. And the cool thing about it is because we have this toml file here, it's not like C where you don't know what files are inside of your package or whatnot. So when you open up any well-formatted Rust project in IDE, everything is known, right? You can click through your methods, you can search through it. All the code relationships are there. It's defined inside of this particular file. And then it's always the case that you either have like a source or a lib directory, which means it's source if it's a binary, lib if it's a library, and then you can look for your main.rs, which will, in this case, since it's the binary, you can be here and look for main, and that's basically it. So that's kind of how you can navigate your Rust code. So this is kmain. Runs here, we have like some check with a panic if something doesn't work, and then this is the main loop of the kernel. That's it. This is the scheduler. That's the whole freaking scheduler right here. You're looking at it. Basically, it says, do I have a task that's runnable? If not, find the next task, repeat. Done, right? Super, super simple. And it turns out, actually, so Zeus is a microkernel. The only thing the kernel does is basically this and some memory management. So the kernel itself is like a few kilobytes, runs out of like 8 kilobytes or 4 kilobytes of RAM, and just coordinates all the applications. And the way the whole thing is structured is with message passing. So when you want to go ahead and say print something, you actually send a message to the print server. The print server gets the message, runs it, and says, I've done printing, and it goes and waits, and it idles, right? So actually, the reason why we don't need a scheduler is actually we delegate it to the system tick timer. The tick timer is actually effective with the scheduler. It's a whole nother process. The kernel can keep, the tick timer can fall over. The system will be quite unhappy because like you're not getting events and stuff. But you can actually, other processes can still run. So it's not like Linux where like if one portion of the kernel falls over, the whole thing stops. We can actually, like it's like the file system can fall over and then we can still be doing debugging on the console.
Is SUSE reported to a system that doesn't have an MMU?
It cannot run on a system without an MMU.
So it does need an MMU.
It absolutely must have an MMU. Yeah, and this is one of the sticking points of getting like on a Cortex-M is they have an MPU. And this is an architectural decision we made early on. We want to build a secure system. And we're like, we have been using MMUs for 30, 40 years to build secure systems. We know how they work. We know all these things. And then there's these people who try to make these proprietary like MPU, like little add-ons and whatever it is. And they're not as well understood. The number of people can develop for it is like I can count on 2 hands or something like this, right? And there's almost no code base and no papers on it. So we're just like, look, we have full access to the source code of the CPU. We're going to build a VEX with an MMU. So it's like, it doesn't make sense. And when we dug into the ARM ecosystem, we wanted to build like a Cortex-M with an MMU. They won't license it to you because ARM charges like a huge amount for A series. The thing that basically defines an A series is it can run Linux. And if you want to run Linux, they're going to charge you a lot more royalty for a core that can run Linux, and the MMU is the product differentiation point. So it's like it's a bright red line. They will never put an MMU in a low-end device because they want to charge you more for anything that can run Linux. Kind of annoying.
So in the RISC-V now you have the physical memory protection.
Yeah, so we have physical memory protection on a page-by-page basis.
Is there any plan to port SUSE into physical memory protection rather than MMU?
Physical memory protection versus MMU. What do you mean by that?
So physical memory protection is equivalent to MPU now.
Oh, the PMP. No. What? Physical memory? Say again?
Yeah, so physical memory protection block in RISC-V.
Yes.
Is the equivalent to an MPU.
That's right, the PMP, right, yeah. So that's what we're asking. No, yeah, we won't use the PMP either. Because again, the PMP, it's not proprietary, it's open source, but again, it's like, the number of people who know how to program for it is like, you know, versus like I can talk, everything I told you about this whole virtual memory thing and the switch to, it happens in Linux, it happens in BSD, it happens in Mac OS, like there are bazillions of OSs that do it, and they're very mature and we know how they work. Whereas if I went to teach you about the PMP, we would get in some arcana about like memory segments and defining these things and whatever it is, and it's, I don't know, I just felt like that was not a good use of effort to try and like, I mean, it does restrict the number of CPUs it can run in. So right now we can only run on this FPGA-based device. But there is another group that's actually ported to an Atmel chip that has a A-series core on the inside. So we actually run an ARM now as well with an MMU. That actually is a thing that is possible. So you can run on a Cortex-A ARM now with SUSE. Let me tell you about the message passing inside Zeus, because we're going to become very necessary to understand this to get to the next few bits of facts about how the Zeus system is organized. Cursor, where are you? There you are. Great. Messages and message passing. It's almost like I intended to be here. So the way the kernel works is that you have a server ID, which is a random 128-bit number. It's different on every single boot. It comes from the TRNG. So the kernel actually has its own TRNG port. It gets cryptographically secure numbers. And the security of the system comes from the fact that it's very unlikely for you to guess this number. So unless you choose to disclose your SID, no one can talk to your process, right? That's the default state. We have a name resolver, so you can choose to register yourself and say, hi, I'm the codec service. You can send me messages, right? And then you can look it up by the name, the codec name, connect to it, and it'll give you its server ID. But actually, you can have multiple server IDs inside of your process space. You can have your private space, your public space, you can firewall it. So we do a whole bunch of stuff to try and make that And the other thing we do when you connect by the name server is that we can actually tell the name server, I will let you connect exactly 2 people to me, right? So we do what's called TOFU, trust on first use. This is like SSH, do I trust this key? Yes, you store it, and then if it rotates, it like gets mad at you. So we can say, we want to be discoverable, but only by the boot set of processes. We expect 2 people to talk to us. Once those are claimed, no one else can claim us again. So it's another feature we have to sort of restrict access to your programs. Anyways, we have server IDs, and what happens is basically every single process sits in the sleeping state. You can have 30 processes. They basically, that little schedule I told you, they all sit in that sleeping state. And then when a message comes in, say you hit a key or the timer goes off more typically, you'll go ahead and wake up the system. You'll process the message. You can send other new messages, trigger those sorts of things. They go into a dispatch table, get put in the message queue, and then it goes in the schedule to see what's runnable at that point in time. That's the whole like kind of loop system on inside of it. So one thing you'll notice about this is basically async, right? If you do any sort of async programming in JavaScript, the whole system, the whole task system is async. So we actually, it's kind of weird because we don't have an async layer. We don't have a talk IO driver or whatever it is. But we looked at what it would take to do the async layer. It's basically just exposing this API to do it. And actually, we have to undo a lot of this to create the fiction of the standard library calls because they're not async. So we actually have to create with a bunch of synchronous mechanisms to hide our async nature of the kernel. But that's the core mechanism on the inside. And I said I promised not to use my ID, so let's go back to GitHub. Probably by now you want to run some apps. And the place where those are located is up here. So inside Zeus Core, just at a high level, the services are located here. These are all the kernel services. So this is like the Curve 25519 engine, the SHA-512 engine, the graphics server, input method editor, low-level I/O, the PDDB net. Those are things that you probably don't ever really need to touch or play around with, but if you want to look into them, that's where you find the services. That's in the services directory, right? The locales directory have, we'll get into that later, but basically you can actually support Japanese, Chinese, French, and text-to-speech out of the box right now. So you can, if you want to contribute like a translation, you can add a translation. Everything's like made for internationalization and translation. The apps are located here, the apps directory, and we have a few of them that are kind of available, baked into the system. We have a Hello World app. We have the Matrix command line chat app. There's a REPL demo, so you can chat back and forth, like response eval, reply loop kind of thing. There's an app called Transient Disk. So what this is like, it's actually just like it reveals a 1.44 megabyte disk when you plug it into a computer by USB, and it's all in RAM. So if you want to sneaker net some keys from one computer to another and you want to make sure it's wiped, you fire up Transient Disk, you plug it in, you copy your keys to it, put it in another computer, reboot the device, and it's zeroized. So you don't have to throw away USB drives anymore, right? You can use this for that. There's the ball demo, which is just a ball that bounces down around on the screen. And then there is the vault. This is the big Kahuna app right now. And so this one here has the entire, I think Scott was asking about the U2F stuff. We have actually, what we've done is we've pulled in, this is actually OpenSK, which is the Google reference implementation for FIDO2. And so we pull that in and we make a target for that. So we're pretty compliant in terms of, I think, our FIDO2 implementation by the nature of our code base. Let's take a look at what's inside Hello. Let's look at Hello World. What did I put in here? I forget.
Does any given app take over the whole USB port, or do you have multiple concurrent?
Yeah, multiple concurrent. Yeah. So it can, but you can only have one endpoint active at a time. So you can say I'm now currently transient disk and can switch to the vault, and then now you're a FIDO2 interface. But yeah, it's not. But we can, for example, have both keyboard and serial console available if we were to reveal both descriptors at the same time. So it's like really how you set the descriptors. Yeah, okay, so this one just prints hello on the screen. It's literally like a little hello world dialog box. So you get to the loop, and so this is that loop structure I was talking about. You receive a message from the kernel, you do a dispatch based on the message ID. If you get a redraw, it'll just redraw and just puts hello world on the screen. If you quit, you quit. That's it, and you terminate the process. That's like the simplest possible program. It does nothing useful at all, right? Just prints hello. We have another app, which is the ball demo. So this one shows how to do like rendering of a ball that bounces around on the screen. And so this one here is a little more complicated. We get a redraw. We have a thread that pumps. And what it is actually the pump thread. Do I have it here? It's not here. The pump thread is probably in this module. Sorry, let me just see if I can find where I put it. Yeah. Okay, so we actually start a thread, and you can see here there's a standard Rust thread where we do stand thread spawn. So it's just a standard Rust thread call. And in order to do the animation, we have to continuously say what's the rate of animation. So this here just sets a timer to run at some interval and says move the ball position, and just keeps on doing that to itself over and over again. If we don't have this pump thread, nothing runs, right? You have to have that as one of the threads that gets spawned. And then that sends a message to the main thread, which calls redraw, which then causes the ball to bounce around the screen, that sort of thing. So that gives you a general idea of how it works. So one of the cool things about doing development is that we have multiple emulation modes. So you don't have a precursor maybe, but you can still write Zeus code, because we didn't do, say, cargo x task run ball. So cargo is Rust's package manager. So you cargo build, cargo run, that's how you kind of invoke Rust, right? Xtask is like makefiles, but Rust versions of makefile. So Xtask is our makefile script. And then we have a verb, which is run, which is to run in the local emulated mode. And then we can specify the apps. So we can say, I want ball and I want REPL. So what this will now do is it's going to go ahead and on my slow laptop, build the entire system from source, and it will actually run it in what's called hosted mode. And so in this case here, I'm running the kernel, all the surfaces, everything locally on my laptop with an emulated screen. I'll show you what it looks like in a minute when it finishes running. And so you can actually develop most of your UI stuff in this mode without ever having to load anything onto a precursor device itself. If you actually start getting into hardware, we actually support Renode, which is a near cycle accurate hardware emulator. And Zobs, who's the collaborator who did a lot of the work for this, made the Renode emulator really, really, really accurate. You can do a ton of you can do networking, you can debug the standard libraries on it, all sort of stuff. So if you want to do that, so you have a lot of options to develop code without even having to touch hardware. And then you have finally build for hardware target, and you upload by USB or by the JTAG interface to do things. So this is a slow little laptop. It takes a couple minutes to build the whole kernel. You can kind of see all the modules that's building along the way. Maybe while it's building, I'll say, do we have any questions at the moment?
The possibly deniable.
Database, yep, okay.
Where does that fit into all of this?
So the PDDB is a service, and it slots into the standard library where the file system would go. So normally you have std.fs like open, std.fs close, and what that does is that it will create key value pairs inside of a database which has plausible deniability. And the reason why we call it plausibly deniable is that it has a property where if the database is in its secured state, no one can prove or deny that they have secret data inside of it. The thing starts initially just full of random data. And then as you allocate data, we have a mapping system to map out pages randomly inside with your encrypted data. all the ciphers that we use have this property where the encrypted data is indistinguishable from random data. And so then as long as you don't reveal your basis password or your key to that data, if someone says, give me your device, I'm going to dump it, I'm going to analyze it, you can say, no, really, I've given you all my passwords, right? Like, you have all of them. They can't say, no, I think you have more passwords based upon the amount of free space you have available or how the thing's behaving. That's like not a thing that they can do. So that's the idea behind the plausibly deniable database. Oh, it finished building, but it put the window helpfully over here. So this is what you get. You get this emulated window. This looks like the UI you guys are just playing with. And we can interact with it right here on the screen. So we can go ahead and switch to app. And we can go to the ball demo and see this is what the ball demo does. This is like the thread pumping along and moving the ball on the screen and it's bouncing when it hits different things on the wall. We can switch to the REPL demo. And all the REPL demo is just, you know, it tells you what commands are available. There's only one command available and you just type stuff into it. And it's like, you can basically, the idea is you can just like add commands in here. So if you want to build your own little shell interpreter, it's like a thing you can hang off of it. And every single app, you can see here, there's like these little tabs that are showing in the bottom of your history that you type. That's just inherent in the system. So you don't, that's not part of your app. That's the input method editor service. So you can basically get a history of the last 4 commands you type. You can just punch the F1 to F4 buttons to recall those commands. So yeah, that's kind of like how you would build an app and play with it. So you can do that without, like, this is not, you don't have to have a precursor. You can actually start playing with the Rust code today. If you want to go ahead and add your own app, you basically would start with one of the templates that we have. I would probably just say fork it. And the easiest thing to do is just take one of the templates and start editing inside of it, because there's a little bit of complication in adding your app to the system. But if you actually want to make a full app, you have to add it to the manifest. And there's a JSON file here where you say, this is the name of my app, this is the name of the context, and then you have to give it the name of your app in all of the supported languages, right, ideally. Some people just leave them blank for languages they can't translate, but it's nice if you just throw in a Google Translate and put something there so like it doesn't break our CI system if you try to merge it in. And then this will always look for, yeah, this one here, we don't have the translations for this one. It'll break if you go ahead and try to like have that in Japanese. But then, yeah, you would just add your directory here, put your app inside of it, and then it'll actually automatically pick it up when you say cargo x run my favorite app, and then it'll go ahead and find your app in the manifest and build it into the system. It'll be in the image. So that's running in hosted mode. If you want to build for actual hardware, you just do cargo xtask app image, and then, you know, my app, like you build it. I'm not going to run that because it takes a minute to build it and it'll flush the cache. And then what it'll do is it'll create a zeus.img file, which you can then upload by USB into your device. And then you can, it takes about 2 minutes if you have an Intel CPU. It takes 30 minutes if you're running AMD or Mac because of some quirk of the USB drivers. So USB is a little painful to upload the images on, but we haven't been able to figure out that bug yet. So that's kind of building apps for it. If people want to go ahead and start playing around with it, they can do that. Is there anything else people want to sort of dig into in particular on this? I mean, there's a lot of different topics to go into, so it's like.
Just on apps, what is the most crazy app that you have seen and say, wow?
Probably the Vault app is the killer app, right? And that's the one that I kind of, you might have saw in the unit I was passing around. It has a TOTP, it has the passwords. The passwords actually support like BIP39 natively, so if you're storing, I can show you the UI for it, but basically it has like a live, the BIP39 is a list of 2,000 words that you can fix, so actually as you type them in, it will correct the words for you and autocomplete them, and then also it will like compute the checksum, so if you typed in your word wrong, it won't let you accept it, these kinds of things. So it has like a bunch of like hooks and features in it for password management. And it does U2F stuff. So.
Do you see this debug infrastructure becoming network available, or like removing a way that makes it more practical to have like your thing just plugged into it to do some target?
The debug infrastructure, what do you mean?
Right now, all of the Cargo X-task stuff requires the physical attachment to the device, right?
No, so our Cargo X-task run is all running on this device. My precursor is not plugged into here. That screen is actually fully emulated using OS native calls.
Right. But if you wanted to debug a running Zeus process on a physical device, you would have to have the physical debug.
That's right. Yeah.
So do you think that infrastructure will eventually become more like, Android development or something, where you just have your precursor in your laptop?
So what we do typically, if you need to debug something on a physical device, we use Renode. We go into the emulated mode, and that one you can just stop and dump the whole. It's like way more powerful than debugging on a device, because debugging on a device you have to go through GDB and step, and it's like annoying. Renode, you can be like stop, dump everything, like your God mode. It's like much more powerful to debug in Renode. So if we can, we'll debug in Renode.
How about the kind of inverse where you're just like running a remotely downloaded chunk of code from the device itself?
You mean, can we like basically have a runnable app that we get from remote? Yeah, we don't support that yet. We have to build it into the image because there's a whole loader and signing stuff that we have to deal with. So we don't have like loadable apps per se.
You can't set a sign for something.
Yeah. We don't have that yet. That's something that's like on the wish list of things that we're probably going to introduce at some point in time, because people want to be able to do. It'll be faster if we don't have to like copy the whole kernel over. If you're just doing an app update, it'll be way faster over USB. But we have to do a lot of rework on the loader and the OS dispatch system for that to work. Yeah.
So when you run Renode,
I'll turn on the lights here.
when you run the Renode emulator simulator, how close does it correlate to the real device?
It's really pretty solid. Yeah. Like yeah. There are very few. It simulates bugs and crashes really reliably. Yeah, it's really impressive how well Zob's tuned in Renode to emulate device. It's like bug accurate, which is really hard to do. It's a lot of effort to get that level. Oh really? Okay. All right. Okay, I thought maybe. Well, I think it's like, unless people want to like, if you have a device you want to actually start hacking on it, I'm very happy to like sit down with you and start hacking it, but I also recognize there's a lot of interesting things going on here. So if you don't actually have a device and I've kind of talked through everything, feel free to like pop out. But if you want to actually get into something in particular, I have all my hardware here to go ahead and develop. We can log in, do all sorts of stuff, whatever it is.
So I assume you've been working on the Vault app lately, right?
That's been, my focus.
Do you want to just like show us your features?
Sure. Yeah, I can show you what Vault looks like. So probably easiest to show it on the screen here in hosted mode, because we can do that as opposed to trying to do anything else. Let me see. Cursor. Cargo X-task run Vault. Okay. And then I'll turn off the lights so we can see the screen again. Maybe it's more interesting if I had some test records in there, but.
How would you cross the boundary from the RISC code for the ETL to the accelerator that you have on the FPGA? So you have a very large scripture complex that
I can show that to you. Right. We'll do it on the browser, because then you can find it later on instead of in my weird environment. So that would be inside apps. Core, services, engine 25519. This is the driver for it. There is, we have actually a pretty good online data sheet, which shows you like the architecture of the engine, all the math on the inside, how to write code for it, theory of operation, blah, blah, blah. This is all there. You can find, knock yourself out, right? The actual driver itself. So when we have drivers, you see this is the structure here. We have both a main and a lib. What it happens is there's a main program that runs, and there's a bunch of library APIs that go into it. Probably better to start with the lib side of things. So then we have like, you create an engine 25519 object. That's what you do. You create a new one of those. And then on the object, we have methods like start a Montgomery job. So this will do a Montgomery multiply, and it has some data structure for it. And it passes like all the parameters through the system to the main function. So then that thing is packaged into a message. And so one of the interesting parts is that that's a memory message, and we use the virtual memory system to make that very fast. You basically have your messages in your own process space. We don't actually copy the data. We actually swap the page table mapping. So what happens is you had that page of memory in process A. You want to pass that page of memory to the engine 25519 thing. We actually just remap the page table into there. And so then there's a page table remap without copy. Now there's a hole in the memory space here. It means this process actually can't mutate that piece of memory. It actually prevents, it's actually a very rusty way of doing it. Then this guy can go ahead and operate that structure, mutate the data, pass it back, and then we have the copy back in the native process space. So it's like this.
Yeah, that makes sense. And that means that this main file now issues whatever the wishbone messages.
That's right. Yeah, this has all of the there's like these assembly opcodes for the different like curve 25519 operations. It loads them into the engine. So you self.copyreg job.blah blah blah, and then calls self.mp start. Yeah, so this is an example of a very low level call. We don't use, so most Rust people use what's called the PAC library, peripheral access crate. It's from the TALK project. I personally hate it because I'm a C/hardware guy, and I find Rust syntax really laborious, right? If you use the PAC crate and you want to write data to a register, you have to use a closure. If you know what closures are, so it's like you have to do like double bar this, pass this thing in with an argument. It looks really awful and heavy. It compiles down to just one store. Trust me, right, is kind of what it looks like. I don't like that. It's too much magic. So I have like this, I built my own little crate. And so you have self.csr. WFO means like write field over, like writing the whole register over, not just field up, like it's writing the fuck out of the register, right? So it reminds me that's going to happen. And then we have like the actual hardware mapping here. That's the actual register window and the argument. That's it. That's a low level call for the system. Yeah, that's what it looks like. Yep. Yeah. Okay. Yeah.
Did you consider implementing that as a RISC-V instruction set extension instead of like something?
It's a little bit too complicated for that. AES is actually a RISC-V instruction set extension. That's actually like a custom RISC-V opcode. And it's AES, you almost have to make a RISC-V instruction set extension because the cost to context switch to pass 128 bits of AES and then decrypt it and then pass it back is more than the decryption operation, right? Just the passing of that little bit of data, running the engine is like a lot of overhead. So with a RISC-V instruction set extension, it's in your native process space, you run it, and then you actually get an acceleration. But just message passing overhead is like huge for AES. I mean, you can do like per blocks and whatever. There's a whole bunch of like things you can do if you're doing bulk data, but it just turned out that instructions are way better. Whereas this here is like curve 255 was so heavy, Montgomery our Montgomery whatever multiplier, whatever it is, huge block of data that we can afford all the marshalling, and we still get a substantial speed up. Yeah.
So in order to kind of try to support, virtually you have to do it with Zeus in general. Some extensions on the RISC-V processor. Like, is there actually support in the compiler, or do you just inline assembly it when you need to?
Oh, when we do the extensions? Yeah, I'll show that to you in just 1 second. One thing I just want to show you, if you want to know where all of the registers are in the system, they are located inside this thing called UTRA lib. UTRA stands for unambiguous thin register abstraction. So that's the thing I just showed you with like the WFO, whatever it is on it. And then this here actually contains the, after some preamble code, this is the full list of like, this is where the keyboard base is located in memory. And then these are the fields for resetting the sock and that sort of thing. So if you ever want to sort of get a cheap like hardware reference manual, it's kind of your C header file version of it. For the RISC-V, you're talking about the AES extensions. That is handled inside.
Do you have like some LightX magic that adds that as an additional target alongside JSON and my SVD and stuff? Or?
Yeah. This all comes out from LightX. So LightX puts on SVD and we turn it directly, and it's all automated. So every time we build the sock, we can get a new SVD file. Yeah. It's all automated in the build system. So if you went ahead and you added like another peripheral to your BeTrusted sock and you put the SVD file in the right place, it'll pick it up and then you'll have those calls automatically. Yeah. So, right. So where is it? This is not the right file. Bunch of. Yeah. So basically, this is what it looks like. We just have these inline assembly calls, which is like, this is the actual instruction and then ret behind it. So that's how we call those individual CPU instructions. So when we write the actual assembly core, yeah, then you see like we see vex AS dec ID 0. This is actually translates to that instruction with those arguments, and then we abstract back up into the standard AES library from Rust crypto. Does that answer your question? Okay. Okay, you wanted to see what Vault looks like. I have to find my cursor again. Here it is. All right. So switch to app, key vault. Okay, so it starts out in FIDO land. There's no keys found because we haven't connected this into a host or anything like that to give us FIDO. So this is what the TOTP looks like. So you can see it has like the little 30-second countdown timer on the top to say how long you have left on your 6-digit number. It gives you a 6-digit number, and every single time you add one of them, you get another entry inside of that vault. And then this is what the password thing looks like. So I don't know, I had some, you can see I was just making bogus entries for testing things. So close menu, F4. So we can go ahead and edit one of these items. And so this one here, like the way we do BIP39 is that if you just put BIP39 as the first words here, it actually will show you the password rendered as BIP39 as well. So it stores the hex string and then gives you the BIP39 code, as it may be. If I want to go ahead and create a new entry, so add new item, name it TEARDOWN, bunnie, blah, blah, blah. So there's a password generator here you can use. It suggests you one, or you can type BIP39 to generate a BIP39 password. If you hit backspace, I can say how I want the password to be 16. I can say if I want uppercase letters and numbers only. So instead of symbols, in case you have like some weird site that has these restrictions, and it'll give you a new random one. This is all using the internal TRNG, blah, blah, blah. And we've created like that entry. I can now add another item, TEARDOWN BIP39. This one might be a little painful to work through because I don't have a BIP39 code, but if I do, now I can go ahead and say like, you know, go ahead and autocomplete, you know, whatever, a bunch of BIP39 characters until it's acceptable. And then I can go ahead and say, actually, no, I don't want to do that anymore. There we go. And it just aborted out of that flow because I don't have a BIP39 thing to put into it, but it'll validate the whole thing for you. This thing also has, when you use this in U2F mode, FIDO mode, most tokens, when you plug them in, they will just show you a little flashing light and you don't know what program called it up. This one will actually print the relying party's ID. So if you're trying to log into like, you know, fastmail.com or whatever it is, I'll say fastmail.com is asking for your like authentication, do you accept, as opposed to just a flashing light. So that's like a little extension we added. And that's why there's even like this, the UI for FIDO here. Normally you wouldn't list the number of sites that you have, but if you were, every single time you have a residential key or something like that, it'll add it to there. Another feature of this is that it actually works with SSH so that you can actually put the key inside this device. So if you're an SSHing, your signing key can go inside your precursor. It'll make a little fake private key file, which is actually just a pointer to the device. And then it will actually pass the data to the device, sign it, and move it on. So if you want to go from host to host without having to move your private key and you just keep it in the device, you can plug it into another device, disclose the key, the public key and the pointer to it, and then you can use your device on a new host without ever having to have your key touch that host. So that's another feature that's built into the U2F stuff. So yeah, that's kind of the quick penny demo of.
Do you have a way to like actually simulate a USB connection in the?
No, I cannot simulate a USB connection in this mode. And I think we cannot do that either in Renode. That's one of the things we can't do. So USB is a little painful to debug because it has to be on real hardware because it's very real time. I think there's a question back there. Terrible. Yep. So pip3 install precursor updater hyphen upgrade. And it's always good to kind of run it with the upgrade anyways, because sometimes we have bugs that like break previous versions of the things. And then I can say Python 3-m precursor data. And this, what this should do is it should automatically pick up the device and just run the update. In theory, it should be that easy. Let's put it on the .cam and see how badly I do. Okay, so I'm going to run that command. Oh shoot, I lost it. I can't see both at the same time. There we go. So okay, I'll show you what's happening here. Is it's actually gone online. It's identified what the kernel and the loader and the gateway pre-staged all of the items into it. And if we go to the .cam, the screen doesn't look interesting, but it's frozen right now because what's happened is actually it's now in USB update mode. It's in this like special failsafe mode. And then we can watch the paint drying of data copying to your device. Closer. So on a like this kind of device, the Intel laptop, you can see it's probably kind of acceptable times to write updates, a couple minutes, whatever it is. If you're running a MacBook M1, it takes half an hour or something like this. I don't know why yet. We haven't figured it out. But there's some. We use libUSB in Python to do it, and so there's something in the interaction of libUSB and MacBook Pros, and also Ryzen chipsets that cause it to run really slowly. But Intel chipset, it works decently well. So yes, so this is basically the whole downloading process.
Does this help some? When, like, I've gone to this GitHub repository before, but I'm not about like stars. I mainly got distracted by like how many people were committing.
Yeah, is it a dead project or not? Yeah. No, it's a fair thing to look at. Yeah. Yeah, we should probably do like a click here stupid version of it, right? I think the part of the problem is that it is really like too many things to too many people all at once, and and the information is too diffuse and hard to find. And I think now that we're actually getting enough users, I get a feeling for what people actually want to see versus what they don't want to see. There are some very loud people who want things a particular way, and if I cater to them, then like this repo structure gets weird. But then most people are they just want to do it in a particular way, but I don't see them using it that way, and so I don't make it that way. It's like really. So if you're storing the loader, it's the last step. Let's switch it back to the .cam, and let's hope that it all works. Oh, let me go. Okay, yeah, so this has a little QR code you can go that shows you how to reset the device if it doesn't reset. There you go, it reset itself, and it will complain initially that the SOC version is too old because it hasn't picked that up yet. There you go, and now there's a secondary process that goes through where it's updating the embedded controller. So now it is actually, I've staged all the artifacts in memory, but the embedded controller itself has to be updated by the main CPU. So now it's doing that update process, and that takes a minute. So it's now writing the gateware and the firmware from the embedded controller, and it's going to update the Wi-Fi firmware. So it's another process that you go through. It's a bit of a dance to get you from our very first release to where we are today. Everything has been changed. Everything is updated. Everything's terrible. But there you can go. So a couple other things in the UI. There's these little like lines on the back here. These here, every time with something backgrounds, I call it defacement. They're random lines that are drawn to prevent someone from taking. If someone sees your background and tried to give you a fake password box, you would see those lines drawn on top of something that is not supposed to be there. So there's actually a trust level associated with every single UI element, and we tried to make sure that you can't get like a fake, like password UI. It's like someone sends you a BMP that looks like your password box and you type it into the password. So it's like, the whole system is like paranoid code around this kind of thing. So, yeah, so again, paint drying. There's a lot of paint drying involved. And so I'll give you a preview of kind of what happens next. This thing should reboot, and it's going to ask you to do this ritual called setting up your keys. And this is the point at which you have to pick your root password, and you'll pick a boot unlock password later. Right? So you pick a root password, and that takes about 4 minutes to go ahead and re-provision those keys, re-encrypt that. And what you're doing is re-encrypting FPGA ROM to that. And then the typical thing that happens next is you reformat the PDDB. And that takes 15 minutes because you have to write 120 megabytes of cryptographic random data. It takes a long time to generate that much data and format that amount of cryptographic data. And then when that's done, your system is now ready to use. So it's a bit of a journey to get to that point. But we prefer to be, it's all done in the user's hands because the units shipped to you generic. Everything, all the cryptographic stuff is generated by you on your device after you've inspected it. We don't do it in the factory for you. The whole idea is it's done by you in the privacy of your own home on hardware that you trust. Okay, yeah, so this is now, so this is doing the gateware update. So that black, when you see that black screen, that's actually reserved for the highest security processes. So there's only, when you see that black screen, this means like something from one of the most trusted processes doing it. So this one's actually writing the firmware. The actual SoC is being rewritten right now by that process. And now it says, please unplug the cable so I can reboot. Press any key. So I'm going to follow its instructions, unplug the cable, and press any key. And so it says rebooting now. If the system shows no valid keys, error, or something else on boot, you can go and do a hard reset, but it looks like this is working fine. Yep. Okay. So there you go. That's you've now successfully updated your firmware. You're now running the latest stable release. A couple things I'll point out is I said earlier there's this, will it show up here? The screen resolution. Yeah. it doesn't show up. There's a little stipple mark across the very top bar here because you haven't initialized your keys. It's saying that you are booting on developer keys. So if someone swaps out your firmware image after you sign it, whatever it is, that'll show up. That's not your screen is broken. That's a security feature. This thing's asking, do you want to set up the passwords for Precursor? You can say, I'm ready, not yet, maybe later, or stop by, you know what I'm doing. So I'll just do not yet, maybe later. I'll let you set your passwords yourself. And then you go into this mode where we can type on it, and we can say like, help, and it'll show you what commands are available inside of the thing. And we can like check sensors and run factory tests and these kinds of things on it at this point in time. But there's no PDDB. You can't run the vault because there's no place to store data. The whole bunch of things don't work. So it's basically in a kind of a diagnostic mode that I leave. Like I think on future releases, you may not even get this console initially because it's confusing to users. So like, the device isn't working. It's not working. I'm like, well, you have to set up your passwords first, right? But for developers, it's helpful to have this. But anyways, yeah, that's it. That's you're now yeah, updated. Let me see what your battery's at now. The 6%, so we'll let it charge a little bit longer. Let's see, what are this? There's a preferences menu in here. You can do Wi-Fi settings for connecting to Wi-Fi. There's a Wi-Fi kill switch, set up the auto backlight, you can set the keyboard layout, time zone, blah, 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 all that sort of stuff. That's in here. The main reason we have Wi-Fi on this device is because TOTP requires you to have time. And anyone who's built a watch knows that watches without a source of time will eventually desync by like a few seconds to 10 seconds a month. And that's enough to throw off TTP. And so the killer feature for Wi-Fi is NTP. We get time through Wi-Fi. That's why you want to connect Wi-Fi on a secure device. You know, we could probably also write USB drivers that set time or something like this, but since we have the Wi-Fi stack, that's kind of how you get time. So usually what I do is I'll like turn it on in maybe once every couple of weeks Wi-Fi, let it do NTP, then hit the Wi-Fi kill switch and just leave it disconnected. That way I don't have to worry about time. People suggested put GPS in there. People said like, well, there's like that radio signal that is transmitted. You can buy a chip that like. There's a lot of ways you can get time, but time is one of those things that's really hard to get. And so Wi-Fi, we use it. And so that Precursor update is just for updating. If you're doing development, there's another thing called update underscore US Zeus or something like this. Update USB. It's in the tools directory. I can show you where it is. Updating your device. Zeus Core tools and all of the little helper scripts are here. So for example, USB update.py, you would just run this directly. So now we don't have the Python package. You just do, I assume you know what you're doing. This has not been made idiot proof here. And yeah, there's a 39 password array, blah, 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 blah. Let me show you that this is all the commands. So you can say USB update -k, and you point it to your Zeus.img files with your apps on it, and then your apps will show up on your device, and it'll only update that piece. But you can see there's a very like extremely comprehensive list of things you can do with this. It kind of is an all-in-one tool for doing things. I have a small diatribe at the moment. The bit39 list is inside this library because freaking Bitcoin people made a bit39 library, which is fine, except it includes the whole freaking world of dependencies. And you have to be running the latest version of Python. And so like when I use their version of the library, no one could run this script anymore. It was like really annoying. So now I just manually implement my own bit39 word list, so I don't have a dependency upon like the rest of the world to have this one. It's really, this is Python, right? A couple other things, if you want to do internationalization, there's this internationalization helper script, which will go ahead and like list all the translation files, alphabetize them, and so you can go ahead and like add a language a little easier with the internationalization script. There is a backup script here, so if you want to do a backup of your device, which is recommended if you're putting like high security stuff on it. Two things to understand about the device, and this is very confusing to a lot of people. This device, as it is right now, ships with what's called the 0 key on the FPGA. So when you want to run a backup, you'll be like, why is my backup key so low entropy? It's just like 0000000, because you haven't set that key yet. There's another thing you can do where you say, I want to burn the backup key on it, and it is a one-way door. It is like no backseas, you can't return this device because it is a very high security key. You get one shot at it, and but you can do it, right? And I suggest you do it if you're going to put high security data on it. But you should do that step before you run backups, because otherwise anyone can decrypt your backup, right? Once you have that, then you can actually run the backups, and the backups are like I just store them on a regular file server. I feel really comfortable about it. It's all my passwords and whatnot because the key is like in this device and it's nowhere else in the world. And then if you are debugging the PDDB, there are bugs. We have the backalizer, which can analyze your backup and pull things out. So sometimes some people have had some really terrible consequences where maybe they screwed something up terribly or they were developing and they lost some passwords or whatever. The backalizer can usually pull out like intermediate records. The actual implementation PDB, it's journaled. So actually the old records can be found if you know where to look for them, that kind of thing. And then there's a restore script here. So if you lose your device and you have a backup, you can run restore. And the restore will actually, you have to have your original backup key, that key that you burned into it. You're given a BIP39 word list. Write it down, put it someplace safe, do whatever you do with your highest security keys. That's the one key you have to remember. You type that in, decrypts the backup, sticks in your device, puts it with the 0 key initially, but it's all decrypted and you have your data back, right? So you can restore to your device as well. Hopefully that should all work. Yeah. Yeah, I mean, I think we can, it's cheaper to just order another device, but yeah, I mean, if you end up really screwing something up, then I can find this. Okay. I think that's all the time we have, right?